Hello everyone. As you know, the lecture was in Turkish because, as I said, we have to be fast so that we can catch up the topics. But now I will talk in English because I know that you can rewind that video and listen again and again until you understand it fully, even if your English is poor. But I will talk very slowly and one by one so that I think you won't have any problems in understanding the lecture. At the last lecture, we had stopped at this topic, the standard representation. For the standard representation, we can use truth table or a mean term, sum of mean term expression. Why do we need standard representation? Because we want to know whether two different Boolean expressions actually explain the same output or not. For instance, here we have one f which is a and b or a prime, and the other Boolean expression says that f is equal to a prime b prime or a prime b or ab. We have to find out whether these two expressions explain the very same output or not. So for that purpose, truth table can be used. And when we look at the truth table, let me take this laser pointer here. When we look at the truth table, we can see that both expressions result in the same output or in the same truth table. This means that both expressions are actually the same. However, there is a problem about truth table. We have seen that there is a problem about truth table. There may be many inputs, so the truth table may be very large. So for these cases, we need a canonical form. Canonical form means that if the truth tables are same, then the canonical representations of the Boolean expressions must be the same. So for that purpose, we will use sum of products or sum of mean terms expression as our canonical form. In this expression, if you have two variables, for instance, then all the products inside your Boolean expression must be in terms of both a and b. For instance, this Boolean expression obeys that rule. So here we see that each product has both a and b, either b or b prime. It doesn't differ, but there must be at least one literal corresponding to a and b. So this obeys that canonical representation, but this doesn't obey. So we have to change that so that it becomes very similar to that representation, and then we can check whether they are equal or not. If they are equal, this means that both expressions are equivalent. So instead of a prime, we can write a prime and b or b prime, because we know that b or b prime becomes 1, and if I end a literal with 1, the literal comes out. So we can write a prime as a prime and b or b prime. So when we use the distributive property, it becomes ab or a prime b or a prime b prime. So when we compare these two expressions, we see that ab's are same, a prime b's are same, a prime b primes are same. So we know that these two Boolean expressions are equivalent, as we converted both of them to the canonical form. This was already in canonical form, and we converted that equation to canonical form as shown here, and we see that they are equivalent. This was the last example we have seen on that topic, and then we said that we can represent any function by the minterms that are used for that function. For instance, instead of writing h as this Boolean expression as sum of minterms, which is a canonical representation actually, we can say that it is sum of these minterms. 15 corresponds to this product, because this product becomes 1 when a is 0 and b, c, d, e are 1. So this means that this corresponds to 15 as number, and this corresponds to 30, and this corresponds to 31. So instead of writing such a Boolean expression, our canonical form can be represented as the sum of these minterms, 15, 30, and 31 minterms. We have seen that. BCD to 7-segment conversion. We said that for each output we have to find a Boolean expression, and for that purpose, for instance for A, we have to represent each row by using w, x, y, z variables, and then we have to OR the rows which correspond to an output of 1. So the resultant Boolean expression corresponds to output A. So we must do the same for B, C, D, E, F, G. And at the end, we can design a BCD to 7-segment converter. Here, for instance, this corresponds to the first row, and this corresponds to 0010 row, which is that row, and this corresponds to 0011 row, which is that row. So the ORing of these products result in A. So we do the same for B, and we do the same for each of these outputs. And you know that after finding these expressions, we can simplify them by using our Boolean expression rules, including the De Morgan rule. So the basic design strategy is as shown in this slide. First, we capture the function desired by the problem. We can capture that function by drawing a truth table, as we did here, or we can capture that function directly by representing as a Boolean expression. If we capture the desired function in the problem by drawing a truth table, in the second step we need to create Boolean equations so that we can represent the circuit as Boolean equations. And then at the last stage, we implement these Boolean expressions as a schematic or using a hardware design language like VHDL or Verilog. For instance, let's think about that problem. The problem is that we have an 8-bit input, and we want to find out whether there are 3 consecutive ones in this input or not. If there are 3 consecutive ones, that means one coming after the other one. If there are 3 consecutive ones, the output of our circuit must be 1. If inside this 8-bit data, inside this 8-bit input, there is no 3 consecutive ones, then the output must be 0. Well, actually for that purpose, we can draw a truth table. But the problem is we have 8-bit of inputs, as I'm drawing here, and as there is no 3 consecutive ones in this input, the output must be 0. And I must continue on by writing each possible input. Here the problem is that the number of possible inputs is represented by 2 to the 8, because the input is 8-bit. So this means that we need 256 rows in our truth table. And it is very hard, very difficult to draw such a truth table. For instance, let me show the last element of the truth table, which is all ones, which is 255. And here the output must be 1 because there are 3 consecutive ones. All of them can be counted as 3 consecutive ones. Then how can I solve this problem? I can look at the desired function, and by looking at the input, I can design such function directly using equations. So 3 consecutive ones means that either the first 3 bits will be 1, and I don't care the other ones. They can be either 1 or 0. So I put X for them. Or I put X for the first bit, first most significant bit, and put 3 consecutive ones next to that. And again, others don't care for me. It's not important whether they are 0 or 1. As there are 3 consecutive ones, the output must be 1. So I am writing down the cases when the output must be 1. So the other combination that results in a 1 is like that. Sorry for my bad axis. And the other is I put 3x here and then 3 consecutive ones. So I think you get the idea. So I can put 4 don't cares, which means I don't care whether they are 1 or 0, and then put 3 consecutive ones. And the other case is I put don't cares to here and even to that bit, and then I have 3 consecutive ones. So actually I represent the desired functionality by using only 8 different scenarios. So can I describe each of these scenarios by using a Boolean expression? Actually I can do that. First of all, please remember that this is A, this is A, this is named as A, the second bit is B, and then C, and then D, and then E, F, G, and H. So for this row, I can easily write that this row represents the Boolean expression, which is shown as the product of A, B, C, which means that A, B, and C, all of them must be 1, so that A and B and C becomes 1. And I don't care about the other bits, so I don't put D, E, F, G, H as a variable inside this Boolean expression. I don't need them, and I don't know whether they are 0 or 1. I don't care about them. So this can be represented by A, B, C. And the second case can be represented by B, C, and D. And this can be represented by this case means that C and D and E must result in 1. Because if there are 3 ones here, this results in 1. So I continue on like that. D, sorry for that, D, E, and F. E and F and G. And this is represented as F and G and H. So if I OR these product terms, I get the desired functionality for my circuit. So let's see that. Actually, Y is equal to the ORing of these product terms actually. So we directly designed the desired functionality as a Boolean equation. We didn't draw the truth table because it would be too big, having 256 rows. So we directly designed by writing the equation. It's not always easy to see the relationship between the input and the output and directly represent it as a Boolean expression. But when it is possible, you can capture the relation between the input and output as a Boolean equation. So in step 1, actually we captured the problem directly as a Boolean equation. So here we don't need that step because we have created the equation in the capturing stage. However, we need the step 2b, in which we will implement this functionality using logic gates so that we design the circuit. Here you see that this AND is for that A and B and C, this is for B and C and D, this is for C and D and E, and this OR gate, actually it is a 6 input OR gate, ORs all of these Boolean expressions so that we get this Y. So this is the solution for our problem. Now let's think of another case. In this case, we have 2 bits of output and 3 bits of input. And we want to see the number of ones inside our input. For instance, here there is only 1 1, so the output is 0 1, which means 1. And here there are 2 ones inside our number, so the output is 1 0, which means there are 2 ones, so this is 2. And if there are no ones inside our input, then the output is 0 0, which means there are no ones inside our input. So what will we do? We can draw the truth table, or we can find the relationship between input and this bit, because this is one of the outputs and you know that we have to design each output separately. So for that output we have to find a Boolean equation, and for that output we have to find another Boolean equation. So in this case, as the number of input bits is a small number, which is 3, we can draw the truth table. So drawing truth table is more straightforward. So here we draw the truth table, and we know that if there is 1 1 inside our input, the output will be 1, as in these 2 cases, and in this case too. If there are 2 ones, as here and here and here, the output will be 2, and if there are 3 ones, the output will be 3. In order to design that, as we all did in our previous examples, we first start with one of the outputs. So let's start with Y, for instance. Now we know that we can represent Y as ORing the Boolean expressions representing each of these 4 rows. Why? Because these 4 rows result in a 1 at Y output. So here you see that these are all 1. So for the first row, we know that we can represent this as A prime and B and C. Or, I say, for this row, I can write it as A, B prime and C. For the third row, I can write as A and B and C prime. And for the last row, for the last row, when the output will be 1, I can write as A and B and C. So this is equal to Y. So in step 1, I created the truth table, and in step 2a, I created the Boolean function, Boolean equation for the Y output. I should do the same for Z. So again, it has 1, 2, 3, 4 ones. So this is also 1 for Z. So I can represent it as A prime, B prime, C, or A prime, B, C prime, or A, B prime, C prime, or A, B, C. So the step 2a has finished. I have found a Boolean equation for each output. So now I can design it as a schematic as our circuit. But before designing this as our circuit, we can try some simplifications using the distributive property, for instance. For instance, when we look at here, A prime B, A B prime, A B, A prime B prime. I can't find parentheses for them. Let's look at A prime C, A prime C prime, A C prime, A C. Also, I cannot put into AC parentheses. So I can look at B prime C, B C prime, B prime C prime, B C. Again, there is no parentheses that I can put by BC variable. So let's look at Y. Here A prime C, AC, AC prime, AC. There are two AC here, for instance. One is AB prime C and the other is ABC. So instead of Y, for instance, I can write A prime BC, or I can write that A B C prime, or these two terms remained, so I can write them in AC parentheses. Let me take AC parentheses, and here B or B prime comes. So I can write Y A prime BC or A B C prime, or this becomes 1, so this becomes AC. So for instance, I simplified Y. So at step 2a, I will first find the Boolean equations, and then I can try to simplify them so that I can design this by using less number of logic gates. Now, before continuing on, let me erase the ink on the slide. For instance, it does a similar method. It simplifies Y, and in implementing Y, for instance, it uses only 2 input AND here instead of 3 input AND. For that, he couldn't simplify that, so he writes down, he draws the Z as it is shown here. Here, this means that there is an inverter here actually. There is a NOT gate. NOT gate is simplified by using only as a circle. So this means that here I have A prime B C. Here I have A B prime C, for instance. Here I have AB. So Y becomes as shown here. Actually, we have simplified Y in a different way, but Y can be simplified in this way too. And the resultant expression is shown as here. So this is its implementation, and this is the implementation of Z. So now I have finished my digital design. So I have the desired circuit which shows the number of ones in a 3-bit input. Instead of connecting, for instance, if you want to connect the inputs of this AND gate to A and B, you can directly wire it to A and B, or you can, instead of connecting this by wires, for showing a more simplified version, you can write A and B so that we know that this A is connected to here and this B is connected to here. This is done in our previous example. And the second simplification is, as I said, instead of using inverters, we can put just circles behind the AND gate so that we know that this is not B actually connected to the AND gate. Actually, B prime is connected to this AND gate. Or even, instead of using this circle, you can write here B prime so that we know that this is the inverted version of B. Now let's perform another design. In this design, we will try to understand which button inside our keypad is pressed. For instance, this is a 4-row and 3-column keypad. So there are 12 different inputs that may be pressed by the user. Each row is connected as an input to our circuit. This circuit is the one that we have to design now. And also each column is connected as inputs to our circuit. So we want that if 2 is pressed, the output of our circuit will be 0010, which means 2. For instance, if 5 is pressed, then the output will be 0101, so that we understand that 5 is pressed. For this asterisk or star sign, we will output 1010, which is actually 10. So we assume that this corresponds to number 10. And for sharp sign, we will output 11 at this output. So we have to design this circuit. Now let's analyze the inputs. Actually, the keypad works as follows. If one presses to 5, for instance, 5 is connected to C2 and R2, so both C2 and R2 become 1 if 5 is pressed. However, for instance, let me take the eraser. However, if 2 is pressed, then R1 and again C2 become 1, so that we understand 2 is pressed. When we look at the number of inputs, we see that there are 7 inputs. 1, 2, 3, 4, 5, 6, 7. 7 inputs. So for 7 inputs, if we make a truth table, we require 2 to the 7 rows. which is actually 128 rows. 128 rows. So this makes a huge truth table to draw. So how can we solve that? Actually, when we analyze the input, we see that the input comes in pairs. What do I mean? I mean that if 1 is pressed, R1 and C1 they become 1. If 4 is pressed, R2 and C1. If 7 is pressed, R3 and C1. So I have 12 different cases only, as I have 12 different buttons. And lastly, if nothing is pressed, the output must be 1, 1, 1, 1, which is 15. So we can say that there are 13 different cases. So for 13 different cases, I don't need a 128 row truth table. I can only draw a 13 row truth table, and by this truth table I can perform my design. So here, as the truth table suggests, if R1 and C1 they are 1, if R1 is true and C1 is true, this means that the output will be 1, because R1 and C1 are true means that 1 is pressed, so the output will be 1. If R1 and C2 are 1, then the output will be 2, because this means that 2 is pressed. I will continue on by filling the rows of my table, and I will only require 13 rows, including this none row, because I have 12 buttons, and also the last case is none of the buttons are pressed. And in this case, I will output 1, 1, 1, 1. So let's start with this W. Now you already know that if we have 4-bit output, this means that we will have to find 4 different Boolean equations, each corresponding to one of the outputs. So let's start with W. We can write W by looking at the rows in which W becomes 1. So one row is here. So W will become 1 when both R3 and C2 are 1. So I will write this as R3 and C2. The other case, when W must be 1, can be presented as R3 and C3. The third row that results in a 1 for W can be presented as R4 and C1. And the fourth one here can be represented as R4 and C3. Because in this row, W must be 1 if both R4 and C3 are 1. And in the last row, I know that none of the buttons must be pressed for that row. So I can end the nuts of R1, R2, R3 and R4. Actually, I know that also C1, C2 and C3 must be 0. But if all rows result in a 0, this is enough to conclude that none of the buttons are pressed. So a better design would require, instead of 4 variables, we could use the primes of, actually I should raise that too. We could use the primes of the columns, because I know that if C1, C2 and C3, if all the column variables are 0, this means that none of the buttons are pressed. So when none of the buttons are pressed, C1, C2, C3 will be 0 and W will be 1 as desired by this truth table. So we do the same for X, Y and Z. So let's see the result. Actually, the result is same as our equation. The only difference is here he used also the row variables, not only the column variables. But as I said, we don't need that, because if all 3 column variables are 0, this means that none of the buttons are pressed without looking at the row variables. Because any button has both a column variable and a row variable, and any button pressing makes both the row and column variable 1. So by only checking the column variables, all of them to be 0, means that none of the buttons are pressed. We don't need to also check if row variables are 0 or not. So the same is done for X, Y and Z. So we, from truth table, we can go to the actual equations, and from equations we can design our circuit as a schematic. So our digital design finishes like that. Actually, for this lecture, I will stop at here, and the next lecture we will continue on from that slide.